This antenna shouldn't work as well as it does. It's mostly empty space. It weighs about nothing, and yet it performs as well as a solid wire that's about 10 times heavier. And today I'm going to show you how I built it. So, super quick background. I'm an amateur radio nerd, and I'm wanting to do some long distance projects on the high frequency or HF bands, which means long wave, 10, 20, 30 meters and longer, which usually means a really big antenna. The kinds of antenna I usually use are a category called end-fed long wire, and that means it's a long wire and you feed it or plug it into your radio at the end. Sometimes in radio you have really complicated names for things, and sometimes it's really nice and simple. So you might think, well, there's not much to design here. It's a long wire and you just attach it to the end and you're pretty much spot on. There are actually just two things we care about in a long wire antenna. Well, three, but the first thing is how long it is, and the second thing is how thick it is. And where I find it gets interesting is we start making really big compromises with reality. There becomes practical considerations, things like the weight of the antenna or the size of the garden or yard that you have to fit it in. The third thing is actually how high you get the antenna as well. And there's lots of maths and things about reflecting off the earth, all kinds of fun things. But we're going to focus on the first two, length and diameter. So, thing number one is the wire needs to be of a particular length for it to resonate nicely on the frequencies. So think of this like a flute. If you make it random lengths, it will naturally sound a random pitch. But the right length, it will make the notes you expect. Or you think about a slide whistle where you can dynamically change the pitch by changing the length of the flute. In this case, I won't go into the detail of why, but the length of this antenna is going to be 8 meters, 86 centimeters, or as close as I can get to that. And then it will resonate on the amateur bands. Now we've picked our resonant length, the second thing is the diameter. Here, thicker is better. The thicker wire will intercept the most amount of wave energy, but the cross-sectional area of the wire grows with the square of its radius, and so its weight does too, not to mention its cost. Effectively, a 10 centimeter wide solid copper rod gets very, very heavy and expensive over several meters length. Copper is 8 tons per cubic meter. But physics has a trick for us. It turns out we don't need most of the solid block of the antenna. We actually don't need much of the middle at all. The electrons for the field interaction happen on the outside, where the free electrons can be furthest apart from each other. So we can actually hollow out the inside of the wire. It also turns out we actually don't need much of the outside either. In fact, we can slice this and get rid of most of the outside, and we end up with a cage. And this is empirically about as effective as having a solid outside. But now we're running at a fraction of the weight, and so we have a cage antenna. Cage antennas used to be much more popular, especially on things like ships. But when you're looking at some of these photos, you have to be careful you don't misclassify a cage antenna with a multi-band antenna, which looks similar, but the wires are different length on a multi-band antenna. This is actually my second cage antenna I built. The first one was good, but it had lots of mechanical issues, and I built it not at fantastic resonance length, so this time I wanted to solve some key design flaws. The original length I tried to go for the longest wire I could fit into my garden rather than going for the natural measured length. This time it's going to be exactly 8.86 meters, and that will resonate really nicely on their different amateur bands. The second one is the structure integrity. Previously I used flat spacers to keep the wires apart, and these had several issues. They would slide up and down the wire, and I wanted to solve for that. And secondly, they would actually twist on the other axis, which makes the cage smaller, and it would actually sometimes twist all the way through, which cause all kinds of kinks and twists and turns. And when you introduce a turn into a wire, that's basically a coil, which means that you start having interference with itself and impedance on the wire, and you don't have a good solid baseline to work from. Lastly, the size was an 8 centimeter wire, and I used 6 strands on my previous wire, and I thought this would be a good time to take up a notch, so I'm going for a 10 centimeter and 8 strands of wire. Looking at the twisting problem first, the obvious solution was to use fatter spacers. This wouldn't be so easy to twist, or small pipes, but I realised these would be hard to print, so I quickly evolved the idea of using some form of spider shape. With 3D printing in mind, my design actually evolved into these hourglass shaped design, which I printed in 2 halves and glued together. For the ends, I designed a couple of iterations of end caps, and these also had to be attached to something to take up mechanical strength. The idea is that down the centre runs a non-conductive length of thread or rope that will take the weight of the antenna, and then the outer side will be the actual antenna. Printing these out and beginning to put it together, I quickly found the first problem coming back. When I tried to tie the expanders in place to prevent them sliding up and down, the knots on the thread actually kept tilting the expanders away from straight, and they were no longer coaxial. So I decided to do something a little bit stupid, which actually turned out to really save my ass. Instead of tying them on, I would instead let them move, and I now 3D print a set of spacers that will sit down the thread and force these to keep apart. So I've got lateral spacers as well as the horizontal spacers. This decision turned out excellent because even though I picked these most unstretchy thread I could find, it still actually stretched over the 8 meters by a quite significant amount. But with the spacers, the entire antenna length is fixed. Once the centre line was threaded, I now thread the outer wires one by one, and even took incredible care, I did manage to cross thread one or two of them, and so I just undid those 2 wires and rethreaded them. It was very simple. This was all hung up in my well, through my lounge and through my kitchen and into my conservatory. But once that's all done, we managed to get outside. Everything is coaxial and straight. I did find as I was building this that putting too much tension on the wires, I could actually bend and compress the wires, so I had to be really careful at that point. It was a lot more tricky than I thought it would be. And then and there is a different amount of weight, and so you do find it does compress slightly at one end, but overall the distance is about right. What we can now do is test the performance of the antenna, not just empirically, but actually with a vector network analyzer or a VNA. When I started in radios, these things were incredibly expensive. There were tens of thousands of pounds, but now the price range has dropped massively, and they're in the sub $100 region, and they work really well. So we can plug it into the antenna and we can test them with various bands to see what the standing wave ratio is. SWR is a weird measurement that ham people use, and the professional communication engineers don't really use that. But basically, it's a really nice figure because it's simple to understand. The lower the figure, the closer to 1, the better. It does change for different frequencies. There isn't just one SWR for an antenna. It depends on the frequency that you're looking at. So I've got a series of plots here which show the different frequencies. Now, I'm not worried about resonance in bands I don't care about, so we're only going to focus on the frequencies I do care about. And there's 2 diagrams here. One on top is a Smith chart. Smith charts let you tell when an antenna has too much impedance or capacitance or too much resistance. And in turn, this lets you know the design. So basically, we want it to be, the points to be as close to the middle as better. The closer you are to the middle, the better the SWR. SWR is basically a measurement of how far away from the middle you are. And then the bottom here is the SWR for the same graph. As you can see in all these graphs, they're pretty linear across the band, and also they're very low. They're all below 2. Once you get into 30 meters here, that's getting a bit more risky. So I think we're focusing on the 10 to 20 meter range and having a lot of fun there. As you can see, this antenna seems to be working really well, but the proof is in the pudding. So we're going to cut now to tomorrow morning because it's now nighttime here, and the HF bands all close up at night, which is a separate topic altogether. And so what we're going to do is now cut to seeing, does the antenna actually work for real? Okay, so it is 7:46, 7:45 in the morning here. We do everything in UTC, but because we're in British summertime, it is also UTC here, which makes it easier. This is on the 20 meter bands, which is always very busy, and there's a rare station here going YJOC, see lots of people. On this new antenna, it hears so much. Very quickly having a look at the reception map, you can see it's picking up people over in Australia, it's picking up people over in the far side of the islands over here, Japan. It's also picking up people in South America, which is a little bit strange for this time of day because this is in night time and the sun hasn't yet activated the atmosphere, the F layers. So this is pretty impressive reception. Of course, Europe is very, very busy, which you'd expect, but this is picking up a lot more stations than my old antenna ever did. And just from first impressions, this antenna is amazing. I just did a transmission. I did manage to work a station. As you see here, the number, every 15 seconds it sees an entire page worth on the left. It just scrolls and scrolls and scrolls. Each one of these vertical bands in the top screen is an individual station, and in between those you can see lighter bands. There are bands hidden and hidden, overlapping and everything. If I very quickly show the PSK reporter though, this is filtered just for me in the last 5 minutes or so, and you can see here that I did a transmission, and the people who could see me are just incredible. It is. I was also seen by some people over in New Zealand, which is astounding. I've never been seen by people in New Zealand before. Signal's very weak over there, but it's still just evidence that the thing is working. So I'm very, very impressed with this, and yeah, I can't wait to now spend the next several hours chasing down contacts and long distance. So this antenna definitely worth the effort I put into it. I was very worried to begin with whether or not I'd over-engineered it or spent too long. It was a lot of printing. The spacers took a long time. There were a lot of mistakes made in the way. So yeah, very, very happy and loving it. This is now what you do. You have to chase down these contacts, people you haven't seen before. This person's minus 18. At some point I'll try and work this call sign, or this call sign, but we'll see how it goes. Thank you very much for watching. Hopefully there'll be some more videos coming out shortly about HF, about how the signal bounces, about why I'm waiting for the daylight and why it doesn't work at night, because the gear works at night, so why shouldn't it? But we'll be doing all that in an upcoming episode. So thank you very much. Sorry about the drought of having nothing coming out, but I'd rather put out good quality content than just stuff that was just ticking over. Anyway, see you all soon.